Hello, Paul. Paul, can you unmute? Paul did not join with the Kemi. Kemi, can you unmute and you pray for us? Kemi, can you unmute?
Yes, teacher.
Good. Good afternoon.
Good afternoon, teacher.
How are you today?
I'm fine, teacher.
Good. Can you open for us this session with a prayer?
Let's pray. Lord, King of Glory, we thank you for the gift of life you've given to us. We thank you for our dear teachers. We thank you for our parents. We thank you for our friends. We thank you for everyone that you put into our lives. We pray that you may forgive us where we've done wrong or taken the wrong direction. Oh Lord, forgive us and show us the right direction. Pray for the sick. We pray for all those people out there suffering, they don't have what to eat. Lord, please be their guide. And we also pray that as we're going to study, oh Lord, remember us to learn something and get it by heart, oh Lord. And in the end, may that glory and honor go back to you. In Jesus' name I pray.
Amen. Thank you so much for that wonderful prayer. I'm so glad and delighted for sure. I've enjoyed the prayer myself. I believe God has heard our prayer and He has answered it accordingly. We have hope that all will be fine. Can I see by show of hands those who attended the last lesson? I know Joey Lavis never missed, and even Kemi never missed. Can I see by show of hands those who attended the last lesson? You can raise up the hand. You can raise up the hand. Can I see by show of hands those who attended the last lesson? Okay, Joy Lavins. Yes, Joy Lavins, unmute. Joy Lavins. Joy Lavins, unmute. Good afternoon, Joy Lavins.
Good morning, sir.
It is a good afternoon. How are you?
Oh, sorry. I'm really sorry. Good afternoon, sir.
Good afternoon. How are you?
I'm good, sir.
Oh, can you briefly remind us what we studied in the last lesson?
The last lesson, we looked at calorimeters and we went ahead to look at specific heat capacity and heat capacity. Then we went to calculations.
We saw specific capacity and heat capacity. Then we saw also, did we see the experiment to determine specific capacity of a solid?
Yes.
We saw it, right?
Yes.
Briefly, can you define for us what you said to be specific heat capacity?
Specific heat capacity is the quantity of heat required to raise the temperature of 1 kg, 1 kilogram mass of a substance by 1 Kelvin.
Very good, Joel Levins. Very good, very good, very good, very good, very good. Then what is the SI unit?
It is measured in joules per Kelvin.
Specific heat capacity. Specific heat capacity, the unit?
In joules
per kilogram per Kelvin, right?
Yes.
Okay, good. Thank you so much. Thank you. Thank you. Can I get another person? Thank you so much, Joel Levins. Can I get another person who attended the last lesson? By show of hands, we are using our hands. We raise the hands up, then I pick you. Can I see Benjamin?
Yes, good afternoon, sir.
Good afternoon. Did you attend the last lesson?
Of course, I was there.
Oh, I know you can never miss any of my lesson, for sure.
Yeah.
Now, we talked about determination of specific heat capacity of a solid using electrical method, right?
Yeah.
where we had the solid should be made into a block, and you make two holes. In one hole you fit the thermometer, the other hole you fit the heater, right?
Yeah.
But you said that oil or glycerin must be applied in the two holes, right?
Yeah.
Why would we apply the oil? Why would we apply the glycerin in the holes?
We apply the glycerin purposely for good thermal contact.
Very good, very good, very good, very good, very good. Good thermal contact. What could be the disadvantages of electrical method of determining the specific capacity of a solid?
The advantages and the disadvantages.
The disadvantages, the shortcomings
Of the what?
of determining specific capacity of a solid using electrical method.
One.
Sorry? You can unmute. Unmute. Yes, Benjamin, you have lost him due to network, I think. Oh, good. Let me see. Brett Rama. Brett Rama. Hello, Brett Rama.
Yes, teacher.
You come a little bit late in class, but it's okay. The next day we shall make the class captain to charge you. You know we have the class counselor here. Brett Rama, did you attend the last lesson?
Yes, teacher.
Did you attend the last lesson?
No.
You did
No,
attend.
I
It's
didn't.
okay. It's okay. Fine. Marilyn, can you unmute? Marilyn, can you talk? Oh, your network. Okay, fine. So, to determine that, what we do, we are saying, we make the solid in form of a block. After making the solid in form of a block, what you do, you make two holes in that block. After making the two holes, you apply there the oil or glycerin to ensure thermal contact, good thermal contact, and then from there you allow the electricity flow for a certain time t. After measuring the initial temperature, then you measure the final temperature after a given time t. Then you make an assumption that if there is no heat loss to the surrounding, which is not achievable, if there's no heat loss to the surrounding, then the total heat supplied, the electrical energy supplied must be the same as the heat gain by the solid. That's why we had VIT equals to MC into theta 2 minus theta 1. Making C the subject of the formula, you'll find that C equals to VIT over M into theta 2 minus theta 1. If the rating of the eta is given, that is power. Electrical power is IV. So it will be PT over M into theta 2 minus theta 1, where you can calculate the specific capacity. We are saying there is one disadvantage of that. One is that, yes, much as we are making an assumption that there is no heat loss to the surrounding, that assumption is not really very true, because heat has to be lost to the surrounding as a must. It has to be lost. Then if you do the coating or the lagging, you are just trying to minimize, but there's some heat loss to the surrounding. So it does not take into consideration the heat loss to the surrounding and also the heat gain by the heater and also the thermometer. So it makes it not very accurate. Today, we are going to see something which is also interesting. Let me share my screen with you and you see exactly what we are going to talk about. We are going to talk about determination of specific capacity of a liquid. We have very many methods of determining specific capacity of a liquid, one of which is using a method of mixture. Number 2 is using electrical method. Number 3 is using continuous flow method. So those are basically three main methods of determining specific heat capacity of a liquid. And we are to look at all of them. For those who have just joined us today, my name is Teacher Daniel ALIRA. I'm your teacher of physics, the best subject so far in A-level, which I know. You can hardly convince me that physics is not the best. I happen also to be, I also go and teach senior ones. So I always tell them that physics is the only subject, if I'm not mistaken. So if you're doing physics, just know that you're doing the right subject. When you add there some mathematics and chemistry, trust me, you will be the best. So this lesson is made possible by Edify, which is funding it. They're doing each and everything. And Edify is working hand in hand with the Christian School Owners Association of Uganda. And the technology which we are using is designed and made by ICT Teachers Association of Uganda. We pray that God continue to bless all these three organizations, and not only the organization, but also God should bless the parents, your parents, who have enabled, who have provided for you each and everything to study. They have provided you with the phone, with the data, and with all the support. So we thank God for them also. And above all, we thank Him for our lives. We pray that we live to serve the purpose why He has left us. You know, many have already passed on. If you can listen to the radio, people have passed their information, obituary messages and announcements. People have died. But for us, we are here, not that because we are the best, but He has a reason why He wants us to still live. May we please meditate upon the purpose why God has created us. And as we are working, as we are acting, as we are walking, let's walk in a way that will make God happy for us. Otherwise, I thank God, I thank Edify, I thank your parents, I thank you also to make it a point to be here. That's that. For those who have just joined, I've already told you, my name is Daniel ALIRA. And we are going to discuss continuous flow method of determining specific heat capacity of a liquid. Specific heat capacity, our sister Joy Lovins defined it very well, is the amount of heat which is required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin. We say the SI unit is joules per kilogram per Kelvin. Now, when you're determining the specific heat capacity of a liquid using continuous method, what do we need? One, we need 2 thermometers. That is one. We label the 2 thermometers T1 and T2. 2, we need an ammeter. 3, we need a voltmeter. 4, we need a rheostat. We need a switch. We need the heater. We need the reservoir, where the tank, where this liquid is going to be placed. We need the reservoir, and then we need an evacuated tube or a glass, which is sometimes called to be air jacket. Now, after go to all those, we arrange the apparatus as shown below. Hope you can see on my screen. Are you able to see on my screen? Hello, let me know. Are you able to see on my screen? You can give me a signal or you type yes or no. Yes, yes, yes. Okay, I can see. Oh, Marilyn says that she can't hear me very well. Oh, sorry, Bambi. Can the rest hear me well? Please let me know. Am I clear? I don't know. Am I clear? Yes, Jonathan says yes. Oh, Marilyn, teacher, it's not clear. Justin says that it's not clear. Please let me know, people. Maybe the problem is with either my network or your network. I don't know. Let me pick somebody to tell us. Bright Rama. Bright Rama.
Yes,
Can you
teacher.
unmute? Am I clear for sure, Bright Rama?
Yes, teacher, you're very clear.
Oh, then that means that the problem is the network of the other side. Oh, Benjamin says the words on the diagram are not seen. Yeah, they are not seen. I'm going to put them for you. Good. So in determining the specific heat capacity of a liquid using continuous flow method, we have a setup which is like this. We have a water reservoir. There's a water reservoir here. I'm putting it here. May not be necessarily a water reservoir, but the liquid reservoir. The reservoir where the liquid whose specific heat capacity is required is placed. So this is water in. Water in. It may not be necessarily water. If the liquid you are determining is water, then it's water in. If it's not water, then it is liquid in. So this liquid enters inside here. Then when it enters inside here, it meets this thermometer. This thermometer reads the initial temperature, heater 1. Now, what you do, you close the switch K. When you close your switch K, you adjust this rheostat so that the current passing through the ammeter is I1 and the voltmeter reading is V1. Now, you allow the current to flow through the heater. You know, when the current flows through the heater, what happens is that the temperature, the heater heats up. Then that means when this water or this liquid, when it flows from here to here, as it is continuously flowing, it will be continuously heated by the heater. So by the time it comes out from the other side, the temperature is no longer theta 1, but rather it will be theta 2. So you allow water to flow, you allow the liquid to flow until a steady temperature. When talk of steady temperature, we are meaning constant temperature. Until temperature theta 2 remains now constant. Now, when the steady state has been reached, remember the water will be pouring down here. When the steady state has been reached, what you do, you determine the time t for which the current was flowing. When you determine the time t for which the current flowed, you determine the mass M1 of the outflow liquid. So that means that in M1, in time t, you have collected the mass M1. Very good. After determining the mass M1, I like this method simply because it takes into consideration the heat which is lost to the surrounding. Now, the temperature of the body, the temperature of the liquid has changed from theta 1 to theta 2 in time t after passing a current of I1 and a voltage of V1. Now, that means that the total electrical energy supplied, V1, I1, and T1, which is T. The total electrical energy supplied, V1, I1, T. That one I talked about it in the previous lesson. Should be equals to heat gained by this liquid, which is mass of the liquid which has been collected, M1, specific heat capacity of the liquid, C, times the temperature change, which is theta 2, minus theta 1. Close. Then plus the heat loss to the surrounding. We denote it with small h. Heat loss to the surrounding, we denote it with small h. So this is the first experiment which we do. The total electrical energy supplied, which is VIT, V1 I1 T, should be equals to heat gain by this liquid, which is water in this case, plus the heat which is lost to the surrounding. Now, after doing that, what you do, you repeat the experiment. But this time round, you adjust the rheostat such that the current flowing is V2 and the PD is also, the current flowing is I2 and the PD is V2 after adjusting the rheostat. Then you allow water to flow. I want us to be careful here. You allow water to flow until the final temperature is the same as the final temperature in the first one. In the first one, the final temperature was 80 degrees when V was V1 and I was I1. Now you have changed the V to V2 and I to I2. You allow this current to flow until the final temperature is still theta 2, which is 80. So you allow the temperature to, you allow the current to flow until the final temperature is 80 degrees Celsius. Then from there, you measure the new mass, M2, which has been collected. Still, after that, the total electrical energy supplied, which is V2, okay, I2 T, should be equals to heat gain by the liquid, which is M2 now. It is no longer M1. M2 C, remember the temperature change remains the same. Theta 2 minus theta what? Theta 1, then plus capital small h. The rate of heat loss remains the same. Now from there, we can divide this equation by T. When I divide this one by T, when I divide this one by T, I divide this one by T. I also divide this one by T. I also divide this one by T. I divide this one by T. Now, when you look at this T and this T will go. I remain with the M1 over T. M1 over T is the mass per second. So we call that one to be rate of flow of mass, rate of flow of the liquid. Rate of flow, at what rate is the liquid flowing? That is mass per unit time, or mass per unit second, or mass per second. So we give it a symbol, capital M1. Capital M1 is the mass per second. Then this one, H over T, it is rate of heat loss, which we give it to be capital H. Then this one, still, it is the rate of flow, which is going to be capital M, but what? But 2. And this one, still, it is the other capital what? It is the other capital H. That means this equation is going to be V1 I1 to be equals to capital M1 then into theta 2 minus theta 1 close plus capital H. This will be equation number 1. Then equation number 2 will be V2 I2 should be equals to capital M2 into theta 2 minus theta 1 close okay, there is C here, there's our C in M1, then there's also C here. M1C into theta 2 minus theta 1, M2C into theta 2 minus theta 1, close, then plus H, capital. This is equation number 2. Now, from there, remember we are interested in determining the specific heat capacity of this liquid. Now, from there, we subtract equation 2, we subtract equation 1 from equation 2. So we shall subtract this side alone. We shall subtract this side, and then we shall also subtract this side. So here, when we subtract, we shall have V2 V2I2 minus V1I1 to be equal to this side. When I subtract, this side when I subtract, I'll have, you can see that C into theta 2 minus theta 1, they are common. It is here and it's there. So I pull it out. So I pull C into theta 2 minus theta 1 is common. So that means here I remain with only M2. So it will be M2 minus here I remain only M1. I close. Remember, H will go. So what do I remain with? I make now C the subject of the formula because I'm interested in determining the specific heat capacity of this liquid. So making C the subject of the formula, you can easily see that C will be the same as the whole of this one divided by this part only. So it will be V2 I2 minus V1 I1 divided by M2 minus M1 into theta 2 minus theta 1, where the specific heat capacity C can be calculated. There, you have successfully calculated, determine the specific capacity using a continuous flow method. Determining is not a problem. What I always emphasize here, or what I always encourage my learners to know, is the terms which are used. If I say mass per unit time, mass per unit second, that is capital M. Because I may have mass and mass per unit second. If I say rate of heat loss, that is capital H. It is heat loss, which is H, divided by small t, which is time. So if I ask for rate of heat loss, and you already have the heat loss already, then the heat loss and rate of heat loss are related by the equation. Rate of heat loss is capital H equals to small h divided by time. So this is that when it comes to determination of specific heat capacity of our liquid using that. I will not go into other things before I get submissions also from some other person. What if, Benjamin says, what if they give us mass alone and the time alone? Do you have to divide Yes, we're going to see calculations under this. Once I've given you mass, let's say m, so that becomes the small m. Then I've given you the time, that is t. Then you should know that VIT, when you're writing the equation, you should know that VIT equals to m without the time, MC into theta 2 minus theta what? Theta 1 close plus small h. You should know this first. Now, if I now divide all through by t, all through by t, all through by t, that is when this one becomes now capital M, and this one becomes the rate of heat loss. What is important is to know which equation do I write when. So if I'm given mass and time, I can decide to divide by time first. Then if I divide by time, I'll get capital M. So that means I will substitute in the equation VI equals to capital M, and then C into theta 2 minus theta 1 minus theta 1 close, then plus capital what? Capital H. So I have to put it here. That is after dividing all through by m, t. If I don't, then I have to substitute it here. Good. I'm getting submission still. Teacher, what is steady state? Steady state is a state where there's constant temperature. When the temperature of the outflow water is now constant, that's what we mean by steady state. However, we can say the rate of heat loss is the same as the rate of heat gain. You can also talk about that. Then the question is, Marilyn says, is an M1 and M2 the same? Marilyn, M1 and M2 are not the same. Once you change the current flowing, the rate of heat flow, the rate at which the heater is producing the heat is not the same as the other one. So for you to attain the same temperature here, the mass will not remain the same. Hope that is clear, Marilyn. Good. Can I get somebody to submit? Even if it's not a question, you want to submit something, it is better. Can I get somebody who wants to submit something at least? Timothy Grace. Timothy? Timothy? Can you unmute?
Yes, teacher.
Yes, Timothy Grace.
Teacher, I'm fine.
You're okay, good, fine. Oh, I wanted somebody to say something on this also before we looked at the procedures which are taken there. Yes, Joy Lavin. Joy Lavin.
Also, I wanted to just ask something small. You said the temperature remains the same.
You maintain the current. I mean, you allow the current to flow, okay, until this final temperature theta 2, okay, is the same as the other one. Do you get that?
Yes.
Yes, yes, yes.
Like change in temperature, will it remain the same?
Yes, it will remain the same. Because if the inflow temperature, remember the inflow here is the same, it's for the same liquid, right?
Mm.
And we are going to maintain the same temperature here. That means the temperature change will remain the same. Is that okay?
Thank you, sir.
Got it, please. Okay. Bob Muller says, teacher, could you please repeat M1 and M2, the difference? Yes, Bob Muller is saying that when you change the rate of heat flow, I mean, when you want to maintain this same temperature, okay, when you want to maintain this same temperature as before, remember the rate of heat flow was M1. Then when you want to change the rate of heat flow, when you change the current, the rate of heat flow will automatically change. So if heat was 20 joules, this around will be 40 joules. So that means that for the temperature to reach 20, I mean, the final temperature theta 2, if it was 90. So for the temperature to reach 90 degrees Celsius, less what? Less or more mass will flow here. Not the same mass. It cannot be the same mass. Good. Let's look at the procedures now. Okay. We are going to move a little bit faster on the procedures because I've already explained almost everything. So you're saying that the liquid is allowed to flow at a constant rate from the overhead tank. Then you put the switch on, that is closing it, and the system is left to run until the thermometers indicate steady temperatures. Steady temperatures here, we are saying constant temperature. And it is attained when the rate of heat flow is the same as the rate at which the heat is lost. So you close the switch until when you obtain steady temperature. Then from there, the inflow temperature theta 1 and the outflow temperature theta 2 are recorded. Before I continue, I see last towel. Hello, last towel. Your hand is up. Last towel. Kimbugwe. Oh, your network is not clear, last towel.
What, teacher?
Oh, we can hear you now.
Okay, just the teacher. That doesn't mean that theta 1 and theta 2 should be the same. I understood something.
Oh, I just got you. I don't know whether I've got you well. Your network is not clear. But I think you're asking, is theta 2 the same as theta 1? Not really. The theta 2 is different from theta 1. But theta 1 and theta 2, the thermometer, theta 1, will indicate 20 degrees Celsius. And thermometer theta 2 will indicate 90 degrees Celsius. So you allow the water to flow, you allow the liquid to flow until these temperatures are not changing. 20 the other side, 90 this side. They are not changing. Then that's when you take the constant temperatures and you record them to be theta 1 and theta 2. I don't know whether I've answered your question last time. Let me know in the chat. I don't know whether I've answered your question. Good. So you record the inflow temperature theta 1 and the outflow temperature theta 2. Then from there, you record the ammeter reading I1 and voltmeter reading V1. This is V1. Okay. Jonathan says, teacher, you're on and off. I'm sorry for that, Jonathan. Can somebody let me know? Am I on and off, Bob Mola? Bob? Bob Mola? Rama? Am I on and off?
No, for me, I'm okay. I think it's his network.
Okay, please. Fine. Thank you. Okay. Okay. They're saying, teacher, you're very clear, very clear, very clear. Okay, fine. So we're saying you read and record the ammeter reading I1 and voltmeter reading V1. Then after that, you measure the mass which flows per second. This is the capital M which I was using in the explanation. The mass M1 which flows per second. Then from there, you say at steady state, I've already written this, V1 I1 should be equal to M1 C into theta 2 minus theta 1 plus H, where H is the rate of heat flow. Then from there, you will repeat the experiment by adjusting the rheostat. The rheostat is adjusted to vary the current through the circuit until the inflow and outflow temperatures are the same as before. Then from there, the ammeter reading I2 and voltmeter reading V2 are recorded. From there, the mass which flows per second N2 is also measured and recorded. Then from there, at steady state still, I2 V2 should be equal to N2C into theta 2 minus theta 1, where H is still the rate of heat loss. Equation 2 minus equation 1 gives you this. You will have successfully determined the specific heat capacity of a liquid using continuous flow method. Any question before you go to the calculation? Any question before we go to the calculation? Ensure that you have understood each and everything. Okay, can we go to the calculation? Teacher is time also the same, yes. Can you go to the calculation? Okay, they say yes, yes, yes. Good. Let's look at EG number 1. I want somebody, let me see, Benjamin. Let me unmute Benjamin. I'm not seeing Benjamin. Yes, Benjamin. Benjamin.
Yes, sir.
You will get for us somewhere, you're going to be recording some of these values, okay?
Okay, okay.
Yeah, get somewhere, you're going to write and record for us some of these values, okay?
Yeah.
Maybe even Rama.
Yes, teacher.
Can you get somewhere and you record for us some of these values?
Yes.
Make sure you have a calculator, okay?
Yes.
Good, very good. Let's move on. We are going to calculation number 1. The merits and the demerits, I already discussed with you already this one. We are saying the heat capacity of apparatus is not required since the apparatus do not absorb any heat at steady state. Then no cooling correction is required. I've already discussed with you this. Why no cooling correction? Because you take into consideration the heat lost. That's why we repeat the experiment. Then next is that you take this reading at your own leisure. You can set up your apparatus, you go and take lunch, you come back and you take the reading. Why? Once the temperatures become steady, constant, that means even if you spend 40 hours, it will still remain what? Constant. It will not change. So you take it at your leisure time. Then we don't have any heat loss by convection because you saw there was a vacuum which was created. It has one disadvantage. It cannot be used to determine the specific capacity of a solid. And 2, since it needs the reservoir, the tank, you need the large volume of the liquid. Large volume of the liquid is required. So it may be hard to use like mercury to determine the specific capacity of mercury. Mercury is very expensive. For you to buy a large volume, it needs a lot of money. And you know, money is scarce, and so it is very expensive. So continuous flow method, though it's very accurate, but very expensive. So I'm going to post these notes in our Google Classroom. Make sure you copy it and also do the assignment which is there. Question number 1. Please, Bright and Rama, get ready with your calculator and the phone, and the book where to write. We are seeing question number 1. We are interpreting it together. Please help me and we interpret this question together. Oh my God. In a continuous flow experiment, it was found out that when the applied PD was this. So this becomes my V1. Please, Rama, record this as our V1. Bright, record this as V1. In a continuous flow method, in an experiment, it was found out that when applied PD was this, and the current was this, so this becomes our I1. When applied PD was this, and the current was 1.5 amps, comma, the rate, please, I want us to mark this, the rate of flow of the liquid, this is the rate of the flow of the liquid, that means it is mass over time. So that means that it is capital what? Capital M. Remember my mass over time, I indicated it with the capital M. So capital M1 became 50 gram per minute. But the issue is in our calculation, this should be in kilograms per second. So if I may ask, who can tell us 50 grams per minute in kilogram per second? How do we convert it? Can you raise up the hand? Can you raise up your hand? How do we convert 50 gram per minute to 50 gram per second? A kilogram per second. Who can raise up the hand and tell us? Joe Levins, I saw your hands up. Yes, Akim.
Thank you, sir.
Yes.
Divide the mass. We first divide the mass by 1,000, then
yes,
divide the time by 60 seconds, which make up.
Very good. So this will be 50, not so, divided by 1,000. Okay. Again, divided by 60, which is times 1 over 60. Okay, 1 over 60. What do you get? What do you get? Rama, can you press the calculator and give us the answer? What do you get? Rama?
Yes, teacher.
What do you get here? 0 point?
After I first converted the 50 grams to kilograms, then I got 0.05.
Can you divide by 60?
Okay. I get 8.3 recurring.
Exponent what?
Negative 4.
That is 0.0008, okay?
Yes.
83 kilograms per watt, kilograms per second. Thank you so much. Can you record that? That becomes our capital M watt, M1. Is that fine? Good. Fine. Benjamin had also given us the answer. Now, so B1, I1, and the rate of heat flow, the rate of liquid flow is 50 grams per minute. Please make sure it is 50 in kilograms per second. That's why you have divided by this. Now, causing the temperature of inflow and outflow liquid to differ. Do you see this? So the difference in the temperature is 10 degrees Celsius. That means that if theta 2 minus theta 1 equals to 10 degrees Celsius. Please record for me that. Then let's continue with the question. When the PD is increased to 16 volts, so this now becomes the V2. And this now becomes I2. Please make sure you're recording. The rate of flow was 90 grams per minute. So this becomes capital M2. But it is 90 grams per minute. We have to convert it to kilogram per second. Who can give us the expression now? Yes, Joe Lavins. What will it be? Joe Lavins. Who can give us the expression? The value now? Yes, Joe Lavins.
We shall get the 90.0 grams over 1000 times 1/60.
Very good. Now, what do you get? Do you have a calculator there?
Yes,
What do you get?
0.015.
Very good. 0.015. Is that okay?
Kilograms per second.
Very good. That is capital M what? Capital M2. Good. Benjamin is very fast at calculating. He's giving me everything in the chat. I like that. I like that. So we are saying that the rate of flow of this was required to produce the same temperature difference as before. So that means that the temperature difference still remains as what? The before one was 10. The previous one was 10. So the temperature difference still remains as 10 degrees Celsius. Find part 1. Find part 1, specific capacity of the liquid. Part 2, the rate of heat loss to the surrounding. Very good. We are going to calculate from here now. So, in the first experiment, remember they are giving us the rate of mass, the rate of flow of the liquid, which is mass. So that means we shall use the expression V1. In the first case, V1, I1 should be equals to capital M1 C into theta 2 minus theta 1, then plus capital H. Is that okay, everyone? Let me know. Is that fine? Arafat. Is that okay, Arafat? Arafat? Hello, Arafat? Bob Mola, is that okay? Bob Mola, is that okay? Okay, let me know in the chat. Good. Now let us substitute our values. Remember, we already have V1. Rama, don't mute yourself now. Can you unmute Rama? You'll be telling us what to write. Rama?
Yes, teacher.
Good. V1, what was our V1?
12.0.
12 times, what is our I1?
1.5.
1.5. Should be equal to, what is our M1? 0.0083, not so?
Yes.
Are there 3 zeros?
There were, yeah, this.
Good. Then times C, which we are looking for, times theta 1, theta 2 minus theta 1 was what?
After subtracting the whole thing.
Yes.
I hadn't yet calculated for that because you said theta 1 and then theta 2.
No, it was theta 1 minus theta 2, which was 10, okay?
Yes.
Good. When you multiply this side, what do you get? 12 times 1.5?
We get 18.
18, very good. Equals to, then what is this times that? It is 0.003. Then plus what? Plus capital H. Is that okay? There's C here. So when we rewrite this, we can start by rewriting this side. We shall have 0.0083 C plus plus H, okay? Plus H should be equals to what? Should be equals to 18. So this becomes equation number 1. Is that okay, Rama?
Yes, teacher.
Good. Let us go to case number 2. What was our V1? What was our V2?
16.0.
16.0 times, what is I2?
1.6.
Very good. Should be equals to m2.
1.5 exponent negative 3.
That is 0.015, right?
Yes.
Then times c times 10, okay? Then plus capital T, capital H, okay?
Yes.
I want to start by writing from this side, then I go back there. So I will multiply this one by 10. Is that okay?
Yes.
Which is going to be 0.15c, not so?
Yes.
Plus H, not so?
Yes, teacher.
Should be equals to 16 times 1.6. What do you get?
Teacher, it's 1.5.
Yeah, this is 1.5. The current, it is 6.
1.6.
Yeah, times 1.6. What do you get?
25.6.
25.6. So we label this one to be equation number what? Equation number 2. Not so?
Yes.
So what do we do in order to get C and H? What do we do? We solve the two equations simultaneously, right?
Yes.
Yeah. So I want you to use a calculator. Do you know how to solve simultaneous equation using a calculator?
Yes, I know.
Please, can you do that very fast? Let's do that very fast, and you give us the answer. So members, from here, now you solve these two equations simultaneously. Rama, we are waiting for you. Benjamin, you can also calculate for us. What do you get? Fortunate is asking, is M2 0.05 or 0.005? Excuse me, sir, M2 is 0.005. So this is supposed to be 0.005. Rama?
Yes, teacher.
Make sure you make the correction here. So this one will be 0.05. Are you going to answer?
Let me repeat the calculations then.
Yeah, you write, you go to equation, then you press equation number 2, then you start with this 118, this 125.6. I think somebody is already having the answer. Benjamin, calculate, my brother. Benjamin, remember I told you two people to be having a calculator. Where is Benjamin? Is somebody else with a calculator? You raise up the hand when you're done. If you're done, can you raise up the hand? So we are looking for C now and H. Okay, Ida says it is 1134.32. I don't know the rest. I don't know, Rama, what you have to say.
So for me, I have a negative.
Negative. And H is 8.3851. Rama?
Yes.
Can we calculate together?
Yes.
You go to equation on your calculator. Press mode. Are you press mode?
Yes, I'm done pressing mode.
Okay. Have you reached equation?
Yes.
Can you say unknown 2?
Yes.
They're asking for A1, right?
Yes.
0.0083. 0.0083. Have you pressed that?
Yes.
You press equal to, and then you press 1. Are you done?
Yes.
You press equal to, you press 18. Are you done?
Yes.
Well, they're asking you A2, right?
Yes.
A2 0.015. Are you done?
Yes.
1. The next one is 1. Are you done?
Yes.
25.6. What is it giving you?
1134.32.
0.32, which is this one, right?
Yes.
Then another equal to, what do you get as H?
8.58.
8.58. So this is in joules per kilogram per what? Per Kelvin. Joules per kilogram per Kelvin. Then this one is in what? Is in watts. Is that okay, Rama?
Yes, teacher, it's okay.
Thank you so much. Thank you so much for pressing for us the calculator. And thank you so much, everyone, for being part of this. If there's, is it well understood? I see Joy Lavis with hands up. Joy Lavis, you can raise your hand up. Joy Lavis, yes, Joy Lavis, Joy Lavis.
Sir, can we still get it without using a calculator?
Yes, we can get it.
Okay, I would like to see how to get it.
Yeah, you come to this equation 1, okay?
Yes.
You make H the subject of the formula. You take this on this side. Is that okay? Is that fine? You take this on this side, okay? So you will have H equals to 18 minus 0.0083. Is that okay?
Yes.
Then you bring and you put it here. Are you seeing this one?
Yes.
So you will say 0.015C plus H is going to be 18 minus 0.0083C should be equal to 25.6. Is that fine? Then you will get the value of C. Is it okay?
Okay.
Okay, please. Fine. Thank you. Okay. All good, all good. Mary says all good. So if everything is okay, please allow me to tell you that you have a nice lunch. I'm sending the work. It has some prior question. Next week, we are going to continue with the calculation still. There's this assignment which you are going to do and make sure you submit it for marking. So next week, we are going to continue with the more calculation on this. So endeavor not to miss. There are other versions of the calculations under this. So don't miss at all. Otherwise, if all is well, then allow us stop here for now. Have a nice lunch.
Thank you.
Okay. Jasim says, Karim, teacher, why is heat in watts, not in joules? Please, this was rate of heat flow. It was capital H, which was rate of heat loss. It was rate, so it's supposed to be in watts. Is that okay? Is that okay, Karim? Karim, is that okay? Please let me know. Thanks for the lesson. Welcome. Fine, thank you so much. If there's no any more questions, we can go and have a nice lunch. Goodbye for now. Goodbye. Goodbye.